Hey y'all, it's your math teacher, Mr. Boyden, back at it again today, and today we're going to be finishing up what our learning is going to be about logarithms. We're going to go through a couple properties and applications, and that will be all the logs we need to know for IB. Okay, so we're going to start here today with our change of base formula. Okay, what this comes from is back before we had fancy calculators like the TI Inspire. It was really difficult to find the value of things like log base 3 of 2. And certainly we could say the base is still the base and the other two switch place. But in this case, it's really difficult to come up with an exponent that turns a 3 into a 2. So what we would do is we'd use the change of base formula, and simply all it says is if you have a log of some base with some number inside the log, you can break that down into two logarithms divided, and you take this number and you put it up top and you put the base, and that goes in its own log down in the denominator. So for example, this question log base 3 of 2, the way we'd write that out, it would be equivalent to log of 3 over log of 2. And then the nice thing about that, that's something that you can type in a simple scientific calculator. So I'm going to try it right now. Log of 3 divided by log of 2, and I get 1.58 when I do that. Or approximately, I'm rounding. All right. So this same trick works if you use natural logs. So you can take any logarithm with any base and you can write it as natural logs. Technically, any base would work as long as you're consistent. So base 10 on both of these, base e on both of these. It doesn't exactly matter, but those are the two that our basic calculators know how to do. So that's all the change of base formula is. Now go ahead and try these ones and get a little practice. Make sure you know how to type them in. Okay, when you're ready, hit play again and we'll compare. Okay, first one, we get, I'm going to round it to 2.26. Actually, that makes sense. If we did base as the base, the other switch place, we'd get 3 to the x equals 12. And you can just think about this. If you say 3 squared, that'd be 9. It's not big enough. If you say 3 cubed, that'd be 27. Too big. So the answer had to be between 2 and 3, and it happens to fall around 2.26. If you type the second one incorrectly, you should not be able to get an answer at all. In fact, I'm going to put a little sad face there. Let's think about why. This is asking 2 raised to what power would be negative 16. So really what that comes down to is there a way to choose an exponent that will turn a positive number into a negative number? No, there's not. Now a lot of people say, wait, what about a negative exponent? What about the negative fourth power? Okay, let's see. 2 to the negative fourth would be the same as 1 over 2 to the fourth. Okay, that's not the same as negative 16. Or some say, hey, well, what about a fraction? What if the exponent was 1/4? Well, how about that? Let's see. So 2 to the 1/4 power, that would be the same thing as the fourth root of 2, and that doesn't make it negative either. So y'all be advised, you cannot plug negative numbers into a logarithm because there's no way for an exponent to make a positive number into a negative one. All right, let's look at some properties. Okay, these come exactly from the IB formula sheet. I've used U's and V's, so the letters are a little different, the order's a little bit different, but they say the same thing. Okay, the first one, the product property, that is synonymous with what we already know about exponents. So for example, if I gave you x squared multiplied by x cubed, would you know that that's x to the fifth? Would you remember that you can just add the exponents? So this is a case where we have multiplication of like bases that turns into addition of the exponents. Well, look at what we have here. We have multiplication inside a logarithm, and we're allowed to express that as addition of two distinct logarithms. So how would we do this first one? We would write that as log base 2 of 2 plus, so we see multiplication turns to addition, plus log base 2 of x. Okay, we know log base 2 of 2 is 1, so I'm just going to simplify that out. And then I still have the log base 2 of x right there. Okay, what about the next one, the quotient property? That's the exact same idea that we have with exponents as well. When we have something like x to the fifth divided by x squared. Okay, so what you may remember here is that's x cubed, because what we can do is we can do 5 minus 2, or you have 5 x's here, 2 x's there, 2 of these cancel out 2 of those, so there's 3 left. So here we have a case where division is expressed by subtraction. Okay, look at our logarithm rule. Okay, we have division within our logarithm. We can re-express that as subtraction. So let's look at an example. This one, we see division. We rewrite that as log base 5 of 5 minus log base 5 of x. And we can simplify that down a little further. Log base 5 of 5 is 1, and I can't simplify log base 5 of x, so I'll rewrite it. Okay. This last rule, the easiest way to think about it is if I have a log of any base with anything sitting there in the log and that anything has an exponent, I'm allowed to drag that exponent down in front. Okay, and there it is. It's sitting right there. Now, y'all, I haven't mentioned it yet, but it's often not useful to think of these as being formulas that you plug numbers into. What they're better off as reminders that if I see multiplication, I'm just going to use addition. If I see division, I'm going to re-express that as subtraction. If I see an exponent, I can drag that down in front. Okay, so let's look at this example. So first we have to identify what is the exponent. Okay, a lot of people say it's 3. In class, a lot of people also said it was 2. Y'all, you're close. It's not either of those. It's actually both. Okay, so it's log, and we have x, and x is raised to the 3rd power, but you have to express the root as well. So it's the 3/2 power. We can rewrite that as 3/2 log of x. All right, let's do a few examples to gain some practice. Let's try these. Okay, in these exercises, we're going to condense these down to a single logarithm. Now, my suggestion is you pause the video, write them down, try them on your own, and then hit play because I'm going to go pretty quickly through them. Okay, here I see subtraction. I know subtraction's connected with division, and so I'm going to put these together into one single logarithm. Okay, so I get natural log of x over y. What about this one? I see addition, so I know there was multiplication in there, and I see a number multiplied in front, and so we said we can drag exponents down. Well, we can also push exponents back up. So what I'm going to get then is I'm going to get log base 2 of x to the 1/2 power, because the 1/2 doesn't apply to the 2t. And then this addition says I can multiply this and that. So multiplied by 2t. Okay, what about the last one? I see addition, so maybe it's multiplication. Not so fast. We don't have common bases. And if you recall, each of these rules says you have to have the same base across the board on these. If the bases don't match, then you don't get to apply the rules. Okay, so that's just there to say, hey, wait a minute, be careful, always look for that. Now let's go the other direction. Let's expand these. So again, pause the video and try on your own. Okay, what I see here, I see that I have a little bit of multiplication there, and I have a power there. Now, y'all, the thing that people screw up is they go, ooh, there's a power, drag it down right now. You have to be careful. This squared is only applying to the x, not the 5. So we actually have to split that up first. So I'm going to have log base 6 of 5 plus, because multiplication turns to addition, log base 2, or base 6 of x, and then I'm also going to take that exponent and drag that down in front. So that's our expanded form. Okay, what about this one? Natural log of 3x and natural log of y, and a little minus goes in between them because there's division, and I can actually expand that a little more. Do you see what can continue? Okay, I can rewrite this now as natural log of 3 plus natural log of x minus natural log of y. Okay, so that's fully expanded. Now those aren't too exciting. We're just practicing using the rules, but let's actually try to do some problem solving now. Okay, so here's another place where you get to sort of make the call, choose your own adventure. If you are feeling a little bit adventurous, you might want to try these on your own first. We're not going to use a calculator. We're just going to try to simplify them using the properties we've talked about. If you're feeling like you're not too confident, maybe you want to watch 1 or 2 of these with me before you try them on your own. Okay, so we're going to simplify these down. So we're just going to see what we notice. The first thing I notice is I have an exponent, so I'm allowed to bring that down in front. So negative 0.2 log base 3, and I'm not going to write anything else yet, because in my perfect world, and this is a technique you can use, in my perfect world, I really want there to be a 3 right here so things cancel out. Now, we know that the correct number is 81, so I'm going to have to make some sort of a modification to 3 so it actually says 81. Now, y'all, there's a lot of ways we could do that. We could multiply it by 27, that would work, but my favorite way to do it is to raise it to the 4th power. So now what I have log base 3 of 3 to the 4th power. 3 to the 4th is 81, and we remember that when we have an exponent, we're allowed to bring that down in front. Now, that may feel a little weird because we've already done that, but if we have another exponent, we're totally allowed to do it. So what do we have? Negative 0.2 times 4 times log base 3 of 3. Well, log base 3 of 3, we know that's 1. Times 4 is 4, times negative 0.2 gives us negative 0.8. And that's all it is, y'all. Okay, what about the next one? Okay, on this one, I notice a 5th root, And earlier we showed that we're going to express that as an exponent, so let's do that now. So log base 4 of 4 to the 1/5 power. We know we're allowed to drag the powers down in front. So what I get is 1/5 log base 4 of 4. Log base 4 of 4 is 1, so this comes out to 1/5. All right, what about this one? I see multiplication. All right, so we better break that up into addition. So natural log of 5 plus natural log of e, but people, I'm not going to write the root on there. I'm going to write the root as the 1/2 power. And actually, right now, I'm going to drag that down in front right there, because that's going to help me see, hey, natural log of e, we remember from our previous lesson, that's 1. So what do I have? Natural log of 5 plus 1/2. And then what about the last one? The last one's a little tricky. So with this one, I write log of base 9, and what I'm going to think about first is, hey, I'd really like it if that was 9. And is there a way for me to put an exponent on 9 to get 27? Okay, well, spoiler alert, y'all. Yeah, there's a way to do it, but it's really hard to look at it and see, because if you put the second power, 9 squared is 81, that's way too big. And if you put 9 to the first power, that's 9, that's too small. So that exponent probably falls somewhere in between 1 and 2. And if you don't see what it is right away, we probably need a different technique to find that. So one thing we could do is we could write that as log base 9 of maybe 3 times 9. And there's a bunch of ways to do this. I'm just going to show one of them right now. Okay, and then I can split that up. So log base 9 of 3 plus log base 9 of 9. Okay, well, log base 9 of 9 we know is 1. So I'm going to do a little simplification. What we have to figure out is, what is log base 9 of 3? So I'm going to build a little box over here to work in, and I'm going to see. So log base 9 of 3 equals something. The base is still the base, but the others are going to switch place. And so now the question becomes, what do I do to a 9 to turn it into a 3? Well, I can't do squared, that's 81. I can't do cubed, that's even worse. So what could I do to 9? I could remember that the square root of 9 is 3, which means that 9 to the 1/2 power is 3. And if that was x, that tells me log base 9 of 3 is 1/2. So log base 9 of 3 is 1/2. So now I get 3/2 as my full solution. Now let's take a look at some applications. Okay, one of the ones that I like and that I hear about a lot is earthquakes. So earthquakes work on what's called the Richter scale, and if you've watched the news, if you've ever seen an earthquake report on the news or in newspaper, something like that, then you've seen these numbers. So the largest one that I know of that's ever been recorded was a 9.5 in Chile in 1960, and as you can see, it's very devastating. I mean, it's really, really horrible. Back in 1992 in San Francisco, they recorded a 7.8, the big San Francisco quake. And as you can see, I mean, there's significant damage. Freeway overpasses collapsed. There was lots of building damage. People were killed. That was bad. So keep those numbers in mind, though. Okay, this is a 9.5. This is a 7.8. We had one as recently in the Seattle area as 2001, and this was the most dramatic picture I could find of the damage. The main building damage that happened was in Seattle, and this is not a collapsed building. This is a few bricks that fell off of a very old building downtown. You can see in the background all these buildings are still intact. I mean, this awning fell off, but in general the buildings are just fine. We didn't have any freeways collapse or anything like that. So what's interesting about that to me is you get a 7.8, and that's pretty devastating. A 9.5 is catastrophic, but a 6.8 is not too big a deal. Okay, what about earthquakes that have happened recently? Okay, recently, and this is on 9/30/2018, all of these happened. There was a 4.6, 5.1, 5.0, 4.1, 4.5, but none of these really make the news. So what's going on here that a 9.5 can basically wipe out civilization, but a 5 doesn't make the evening news? Okay, well, what's happening is this. The Richter scale is what's called a logarithmic scale. And all that is, it just means the Richter number is the logarithm of the intensity of the earthquake. So what does that tell us? Since the base here is 10, every time the Richter number goes up by 1, it means the intensity went up by 10. So let's think about it. Let's compare a 5 to a 6. A 6 is 10 times stronger than a 5. What about a 5 to a 7? Okay, 5 to 7, that's times 10 to get to 6, and times 10 again to get to 7. That's 100 times more intense. 5 to an 8, that's 1,000 times more intense. 5 to a 9, that's 10,000 times more intense. Okay, and so that's why you don't necessarily hear about these. So some people think, well, you know, I've survived a 6, how bad could an 8 really be? Well, really, really bad. It's 100 times worse. Yeah, it's horrible. Okay, so always be careful when you hear those numbers. They can be misleading. Our brain naturally thinks in a linear fashion. We think if we went from a 5 to 9, that's not even double, because it's not 10, right? But it's a lot more than double. It is 10,000 times worse. Okay, that's going to be our video for today. Hope you enjoyed it, and we'll see you all next time.